Here's Kevin, and he's going to talk about what I would say is a new kid in the block. It's called Peregrine. So Kevin, take it away.
Thank you. I'm the author of Peregrine. It's very new. It's been about...
Just press the button on top once.
How's that?
Beautiful.
Peregrine is very new. It's about maybe 4 or 6 months old. We have it in semi-production mode right now at work. So I think the main question is why and what is Peregrine? It's a MapReduce implementation. It competes with Hadoop, and there's some other MapReduce implementations out there in the wild. It's primarily designed for fast iterative computation, and basically what I mean is algorithms like PageRank, where you're continually doing the same step and eventually converging to a result. I can dive into that a bit later. It supports ranged partition keys. So a lot of Hadoop is the big one. I mean, Hadoop is the big brother. It's 95% of open source MapReduce implementations or something like that. It is basically Hadoop. And the way Hadoop works is you just write files. But with Peregrine, everything is partitioned. And we partition by the key. The reason why this is important for us is that it supports easy merge computations. And so you can merge between 2 iterations. I'll go over that in a minute. Another advantage of Peregrine is that it's we've really focused on performance and making it very fast. A lot of this is because in the last few years, JNA, which is a platform for calling out directly to C functions from Java, that's really matured, and a lot of older frameworks haven't really had a chance to use them. And this actually gives us really easy access to mmap, MLock, fadvise, modern Linux system calls that aren't really accessible to Java. Our initial sort of sweet spot are ETL jobs, extract, transform, and load. We're not really optimized for storing data for long periods of time. 6 months is not. If you want to store data for 6 months in a file, that's not us. You should probably use HBase or Cassandra or even just HDFS. And the other advantage is it's a really tight, small code base. I think last time I measured, if you're looking at HBase and HDFS, it can be anywhere from like 200 to 350,000 lines of code, depending on how you measure things. I mean, I think you maybe get down to 100,000 if you really want to constrain it, but it still doesn't compare to Peregrine, which is only 15,000 lines of code, which is not too bad. Now, you can just keep the whole thing in your head, which is kind of nice. Sort of our core philosophy is that we're just flat out going to cheat. We're not going to attempt to do things that Cassandra or HBase or Hadoop would do. Our philosophy kind of is, the reason why we named the project Peregrine is we named it after the peregrine falcon. It's the fastest animal in the world. It's super small, it's about this big. And it is able to be this fast because it cheats. It basically uses the updrafts from warm air, rides them up into the sky, and then when it sees prey down below, it just does a straight dive. It can do about 235 miles per hour. Again, it's this big and it looks super cute. So that's kind of what Peregrine is. It's super cute and very fast. And so some of the ways we cheated was to completely just carve out things we're just not going to do, if ever. Maybe in the future, but for right now, we're not even going to look at it. Storage is temporary in Peregrine. It's not your primary data store. The fundamental way that you would use Peregrine is you would take something like Cassandra and you would store your data in Cassandra. And then when you have a job, you use Cassandra as the input, extract in the ETL parlance. And then you transform the data, and usually that can be, for Peregrine, that's usually probably, I don't know, 2 to 3, maybe even 50 iterations of the MapReduce job. And then when you're done with it, at the very final step, what you do is you load it back into Cassandra, into like another table. And that way you're able to have the advantages of both worlds. You have a really fast system that's really designed for MapReduce jobs. And then you have Cassandra, which is designed for availability, keeping your data safe and secure. And then you get it's sort of like the perfect Zen. The other way we cheat is we keep the code base really small. And you can just basically keep the whole thing in your head. All the mapping and reading from chunks and working with the system is really easy to integrate with. Yeah, it's really refreshing to work with, especially when you're starting on a new code base. There's not much legacy in Peregrine. We also don't support online node repair just yet. That might be a little bit on the shorter to implement time frame. But right now, what we do is we keep two to three replicas, and when the primary replica fails during a job, we read from the secondary replicas. And the probability, I mean, you could do the probability, and this is pretty straightforward. It's easy for one machine to fail, but to get to a coordinated failure between two machines within like a 10 or 12-hour period, ignoring class failures where you have like a whole array of hard drives of the same vendor fail, it's very, very, very improbable. So we're just not going to even factor that into our design. And I think I mentioned before, the other thing was that we started fresh. There's really no Hadoop legacy in here. We were also worried that some of the changes we would have to make would have to be approved by the Hadoop community. And I'll go into that in a minute, but there's some other MapReduce implementations that have taken the path of modifying Hadoop, and it's worked out well, but there are forks that now have to be maintained. And especially with Yarn, they may never actually get reintegrated back into the Hadoop tree. So that's a picture of Peregrine Philosophy. And they're actually in San Francisco, so there's probably one a couple blocks. In fact, there's a nest over on the AT&T building in a second. Anyway, so what is iterative computation? It's basically when you're joining against the previous result of a job. So PageRank is iterative. You start off with one job. You get the results from that iteration, but the first iteration isn't accurate. And then when you run the second iteration, you get a little bit more accurate, and you keep doing that, and you eventually converge on a result. And if you look at the convergence, it's something like this. And usually what you do is once you're near convergence, you just terminate. Like you have a function that you can push into your code, and when you're near convergence, within like say 5%, you just quit. Google does this with their PageRank graph. When they execute, they do about 50 to 100 iterations, and at some point in time, they will just terminate. Some good examples of this are both PageRank and k-means. The way PageRank works, I'm sort of hand-waving here a little bit, but you initially assign the rank to all the nodes as 1 over n, and then you flow you flow over outbound nodes by using the graph, and then you reassign value based on 1 over the number of outbound links for the node. And you keep doing this, and you keep fixing it up, and for every computation, you get a little bit closer. The way k-means works is that you take nodes and you put them in this vector space, and then you assign basically centroids. And then when you keep clustering, the graph will actually end up clustering like this, and you'll end up with clusters. But for every iteration, you basically come closer and closer and closer to convergence. And at some point in time, you just quit and get the clusters big enough. So why does Hadoop fail for iterative jobs? The way Hadoop does block allocation is not deterministic. So when you go to write data to Hadoop, it basically has a block allocator that says, okay, you've finished with this block, where's the new master for the block? And then we pick new slaves. So the blocks are actually distributed all around the cluster. So there's when you want to read a key, you don't really know where to go. It's sort of just out there. You basically just have to read the whole file. So it makes joins inherently inefficient. There's two ways to solve this. You can sort both files. You can basically cat both the files together and resort them, which is really inefficient. And then you have both values like right next to each other when you're reading both files. Another way that you can solve this is that you can read from one file, and then while you're reading, you can do a remote read of another file. But the problem is that you often have to read excess data because you don't know, if you're reading the second file, you don't know where in that file to read from. So you're often having to just read, maybe it could be up to an extra, chunk size minus a few bytes extra data that you have to read, and it's remote, and it's not free. And because of the fact you'd be using network bandwidth in this situation, from the previous talk, they were discussing shuffling. You can't shuffle while you can't use that bandwidth for shuffling. You're using it for reading data, and it's just really inherently inefficient. So I'm not the only. Peregrine isn't the only MapReduce implementation that talks about this limitation of Hadoop. There are at least 5, maybe a few more that I haven't heard of, implementations that talk about this. One of them is called Giraffe, which is being worked on with Apache. One of them is Hadoop, which is, I think, the University of Washington. It's actually a really good paper. They took a strategy of modifying the Hadoop core. And what they did was they implemented deterministic block placement and some other features that were necessary to implement iterative jobs. Unfortunately, they now have the problem of merging back into Hadoop, which may never happen. I hope it does. That'd be great. But the other thing that this paper does really well is it actually does a really great job in like 3 pages of outlining why Hadoop falls over in this situation. And I think just reading that paper alone for the explanation is worth it. Another open source implementation is called Hadoop Online, and it was very similar, I think, to Storm in some ways, in that they're focused on streaming computations of live data. So they have like a stream interface, and you can put data in one end, and you can get data out, and it has some optimization for online and so forth. And Twister is probably another major one that does iterative computation. It shares a lot of design from Peregrine. And obviously Hadoop is a competitor for Peregrine. Our general architecture, we wanted to keep things really simple. So we have a controller. The controller handles scheduling jobs on worker nodes. It's just a library, and you embed it inside of a process, and then you SSH into one of your machines, and you run it in screen. And then the controller just prints out, it has a scheduler, and it just farms out work to the worker nodes. And then you have a set of worker nodes that run in your cluster, and usually run anywhere from 1 to 16 or something per box. And it handles storing the data, and then running map, merge, or reduce jobs directly on the data as it's sitting locally. We don't do any support for remote reads. That's kind of counter to our design. I think probably Hadoop implemented to sort of bypass the limitations of Hadoop. Merge is one of the main areas that we wanted to innovate on. Yahoo released a paper called MapReduce Merge, where they argued that merge is another primitive that MapReduce implementation should support. Map is the traditional, I have a key and I have a value, and then you emit intermediate values. Those will then get shuffled and redistributed to the cluster, and then you reduce over them. But what ends up happening is if you have 2 files and they're already sorted, you can't merge against them. So MapReduce Merge works really well if you have a previous job, or it could be a previous job or even another database system where the results are sorted. And this way you can take maybe 2 database systems and map over them and merge the results. Or, for what we do in Peregrine, we write 2 files to what we call PFS, Peregrine File System. And you can join directly against both files, and it just does a merge join. Basically reads both keys and moves forward through both the files as we're doing the merge. And there's actually 3 classes that you have to implement: mapper, reducer, and merger. And merger has a slightly new interface. Similar to map, but I'll show you. So extract, transform, and load is primarily what Peregrine is designed for in ETL. Our primary storage in Peregrine is external. Right now, we haven't released this version yet, but 0.55 supports Cassandra, so you can store your I/O in Cassandra, map over it, and then write it back to Cassandra if you'd like. We have a really simple driver interface, so you can just write a new plugin for like HBase or MySQL, for example, and you can do map jobs over for those systems. We've done, because of the fact that we're designed for ETL jobs, and we're not designed for anything else, we are able to do a number of optimizations that are not possible with other systems, because we're doing non-persistent I/O. One of those, for example, is large buffers. We are allocating larger buffers to basically avoid random writes. When you write into Peregrine, Peregrine node generally hosts about 10 partitions or so. And when you're doing a write, what we do is you can write to the writes can come in any order. But what we do is we schedule writes on the first partition, drain that buffer, and then move to the second one, drain that buffer, and we keep doing that. And then when we go back to the original one, the buffer is probably about full. And this way we can basically get much more sequential I/O. We don't support sync. We don't sync very often. That is a trade-off that we're able to make because we're doing ETL jobs. If the job fails, you just rerun it again. It's considered, it's part of our design is that we don't do jobs where some data loss would matter. And we've also built in some optimizations specifically for a Peregrine because we can do extract and ETL jobs. So one of them is extract map, and that is so that way when you're reading from Cassandra, you can just run maps right over it. So there's no intermediately writing to the data to the file system, which is a big performance boost. You can also do extract merge. For example, you can read from Cassandra and merge from Peregrine, which is kind of cool. Although I haven't tested that. I should probably test that. But it should work in theory. As long as they're both sorted maps coming back out of any system, it should work. We also support features like map load, which is when you're mapping data and you emit. You can have that emit go into Cassandra, and then you can extrapolate. We support reduce load and merge load. Pipeline jobs, we try to keep the I/O in Peregrine pipeline to avoid writing to the file system, if necessary. There are a lot of optimizations that can be made by doing this. And if you were to write to the file system, it's going to end up requiring reading it out. And especially if the reduce will end up just reducing the data to really small, it doesn't make sense to write it. And you have to generally write it to disk during the shuffle phase anyway. So why not avoid writing it to file system during the map phase? I know why Hadoop did it this way. Back in the day, async I/O libraries weren't very reliable. Netty didn't exist, for example, and Java didn't have async I/O. I mean, Hadoop was written like 8 years ago, so they just didn't have the ability to do this. So what we do is we do checkpoints during our flush phase. So here is a quick example of this. And the first one would be like a traditional, the simplest way to implement MapReduce, where over here to the right, you're doing your extract, and then you write that to the file system, and then you read that data out during your map task, and then you write that back to the file system. And then do the same thing with reduce. Like this would be your shuffle phase, and then you read that back out, you reduce it, and then you write it to the file system again, right? And then your second job begins, and it reads it from the map job, and it's just a lot of extra I/O. But with Peregrine, what we do is you can see the first step, and we've actually elided the extract and the map, so there's no file system checkpoint. So this is an extract map. And then you can see, we do have to write to disk during the shuffle. So this would be the shuffle phase. And then we in the map function, we emit, and we write directly to the, this is more of a shuffle. It's not really written to a file. The shuffling is a whole system, which is a bit complex. And then the reduce function takes the shuffle data, sorts it, and then runs the reduce function over it. But we can do things like, instead of writing to the file system again, we can do what's called, in this situation, this is called a reduce map, where instead of writing to the file system, you just immediately map over it. And then you can have that map then do the same thing. But you can see, this is clearly much more efficient. This step alone bypasses the whole write and read cycle. So, imagine you're writing 500 gigabytes to the disk and reading 500 gigabytes out. That's not fast. So, trying to get the whole system to perform and avoid excessive IOs has been really important. So, part of the core design is that instead of a normal traditional HDFS store or a GFS store, or even a more rigorous MySQL table or a Cassandra store, we've sort of done a Cassandra store HDFS hybrid kind of thing. They're not really files, they're more of like columnar tables where it looks like a file system, but you write in key value pairs and you just keep appending. And then the key value pairs are stored directly in the partitioning engine. And the way you do writes are you write in these key value pairs to files. The write interface is literally key, comma, value. And this way the partitioning engine can make decisions about where to write the keys based on the key value. I mean, it's pretty straightforward. We do a hash and then we route based on the key. So the advantage of this from the perspective of Peregrine, especially for the job scheduler, is that write positions are deterministic. In Hadoop, they're non-deterministic. You don't know where they are. But in Peregrine, they're deterministic. Now, there is an advantage. I'll go into this in a second. There is an advantage of using Hadoop's decision to take the non-deterministic routing. And that's, you can spread the blocks evenly across a cluster. So when one machine fails, you can do a fast n-by-n recovery, but we've been able to mitigate that problem. So how do we handle this? So GFS and HDFS both support fairly fast parallel recovery. So this is a many-to-many recovery. So let's imagine you have 100 machines in your cluster, and then one of those machines fails. Now, if you do the normal HDFS block allocator, it will evenly distribute those blocks throughout the cluster. So what you're able to then do is you're able to take those blocks and replicate them to any other machines in that cluster. And that's totally fine. In fact, it's a very elegant design if you're just thinking of a single file, single iteration. It's really quickly, you're able to distribute those blocks. But again, it does have this problem. So, Peregrine generally we're not working on this just yet, but we want to be able to provide parallel recovery in the event of a node failure. We have our node failure design and recovery is designed so that way when a machine fails, it's like it has 10 partitions. Those 10 partitions that are on that one host are evenly distributed on another 10 partitions. So this would be a normal partition layout. What we do is, this is a replica this is with 2 replicas. And then, so these are the primary replicas. So there's 17 slots, right? So we just allocate them this way. And then we just offset them basically. So that way when this host fails, we can read from these other hosts. And I'll show you that in just one second. So when this host fails, all these partitions are offline. And then what ends up happening is that normally during reads, the Peregrine scheduler always just schedules jobs over these primary partitions. These are just the backups. So when the scheduler is normally running and everything's marked online, these aren't views, they're not read, they're just written to. But the scheduler just reads from these primary partitions. In a normal job, it would just read from those. So when this node fails, the Peregrine will gossip, and it will notice that node has failed, those jobs aren't being executed, heartbeats are failing. And then so what we do is we schedule these jobs here on the backups. And the advantage of that is that we can, the advantage of scheduling these backups is that we're able to spread the load evenly throughout the cluster. So even though host 002 is serving additional load, it's really only serving about 33% more load. Well, it's 50%. So 50% more load would be high normally. But normally what we would do is we wouldn't run just 2 primary partitions. We would run something along the lines of like a total 10 partitions per box. And that way, when a machine fails, if you're serving an additional partition, you're just 10% more load, and that's fine. And in fact, speculative execution will take care of it. And I was just mentioning that we allow multiple partitions per worker. So basically, what I was saying is that when a worker crashes, they can execute without any significantly additional load. 10% is fine. It's not the end of the world. So now you could see why, if we did something foolish, like just use one partition, why it would take too long. If you had put everything on a 1 terabyte disk and it's 100 megabytes per second, it's 3 hours of recovery time. That's just too long. So with our setup, it's about anywhere from like 1 to 5 minutes, which is not that bad. That's significantly improved over 3 hours, and it's not as good as HBase, which HBase can do much faster, maybe in like 10 seconds, 30 seconds, but 1 minute versus 30 seconds is totally fine for production application. The sort of core is the Peregrine file system, PFS. The main interface is you just write. It's just key value writes. We write all the writes are routed by key. The files on disk are automatically chunked, and there's a configurable. It's usually about 100 megabytes. I think we default to 100 megabytes, and those chunks are basically go right to maps. So every chunk file is mapped, and then we're able to map. The worker reports every time a chunk is successfully mapped. We have some features. This is obviously very similar to Hadoop, but we do pipeline writes where. I'll go to that in a second. We do pipeline writes where the client connects to one of the machines, and then depending on the replication configuration, when we receive a packet, I think we're doing like 64K chunked HTTP, and so when we receive a write, we immediately replay that. There's an X pipeline header, and you encode the client encodes the pipeline in the header. So if it's one replica, there'll be one host there, and if there's two, there'll be two additional hosts in that header. And then we just keep removing one of them. And the X pipeline is routed by priority. And so we will remove that one host and then replay the HTTP chunk that we had on the machine that is in the X pipeline header. All of the I/O in Peregrine, it's all async I/O. We're doing this through Netty. The protocol we're using is HTTP. So in theory, you could write a client, but it's probably just best to use Peregrine directly. All the chunks boundaries are about 100 megabytes right now. So this would be a quick architectural overview of how a client would do a write to Peregrine. So the client sends the writes directly over HTTP to a worker, and from the client's perspective, this is all it's doing. It just takes this write and sends it here. The worker then looks at the X pipeline header and then writes it directly to the worker. Transparently, the client doesn't really know that this is happening. The advantage of this is if you do the math, it turns out to be much more efficient from a topology standpoint. Like, for example, if the client were going to do 2 writes, that'd be wasteful. The gigabit Ethernet port would be uplinked here. The other advantage is that you get to use both. You get to use bidirectional ports, so you get to use the gigabit Ethernet on both, like an uplink and a downlink. And then these are all done through HTTP too. So it's just data replication goes back and forth between those hosts. So another major optimization that we have is that we support this feature called direct shuffling. So the way Hadoop does shuffling, it's not super efficient. What Hadoop does is it takes all its I/O and it writes all the I/O directly to disk. So as you're emitting keys in a local map, it takes those and it spills them to disk. And then periodically it combines them, it reads them off disk. Oh, excuse me. Okay, I believe it writes to a buffer, combines them, spills them, writes them to disk. And then at the end of all the map jobs, a remote worker through the network, reads them off the disk, and then writes them to the local shuffle data, and then resorts them, and then applies the reduce. This is very, very, very inefficient for a number of reasons. One, when you're doing your, when you're first taking your I/O, and then you're writing it locally, and then you're reading it remotely, and then writing it locally again, all that can be removed. And what you can do is, instead of shuffling indirectly on disk, as you're getting the values, you can just look at the key, and I know where it's going to go. I'll just send it there directly. You can just directly connect to the target node. So overall, this is about a 2x performance difference just on the raw math for doing direct shuffling. There's some trade-offs here, specifically with the combiner. I'll go into that in a minute. But 2x performance boost is not bad. In our setup, this is possible because we're an async I/O framework. When Hadoop was implemented, I think I mentioned that async I/O just was not there. You didn't really hear much talk of it, in fact. And I believe that Hadoop does all of its I/O through threads still. So you wouldn't want to create, in a 1,000 node cluster, you would not want to create 1,000 threads. You don't want to have to use a gig of memory just for this stuff. And your Java virtual machine will crash on 1,000 threads. So that's not good either. So you can see why they took this approach, because it allows for very few threads within the cluster. The other major advantage, which actually I realized when I was implementing it, was that because of the fact that you've now broken out into 3 steps, there's the map phase, the shuffle phase, and then the reduce phase. You can only transfer data during the shuffle phase, right? However, you're mapping the data. There's this whole time interval where you're mapping the data and not sending blocks out on the network. That doesn't really make sense. So this way you're able to actually shuffle while data is actually in play. So there's another performance advantage there as well. Another major, this is sort of like a pet peeve of mine, but Java for a long time has sort of avoided the operating system. That if you go to the operating system, that's bad. You're an evil person, and you should be taken out back. But I just don't really buy that. There are just way too many operating system optimizations that you should not bypass. So we as much as possible, we use MMap to open files. And MMap is just take a file and pretend it's memory, and then you can read directly from it that way. It has advantages versus reading the file directly, in that if you did this function called MLock, you can take the page and you can lock those pages in memory. So when you're doing reads from them, you can prevent the reads from actually being paged out from disk. And so for various algorithms, we're actually using this, and it works out really well. Like, for example, in your Java virtual machine, if you allocate, like a, I don't know, like 100 megabytes worth of bytes, like a byte array, at no point in time do you think that that's just going to go away. So with MMap, that can happen, and your performance can fall. But with MLock, you can actually lock those pages in memory and prevent them from being paged, which, depending on your application, it could be beneficial to have them paged out, but in a lot of the situations, I think it makes sense also to lock them. The other thing we did was fallocate, and Hadoop is now getting support for this, which is nice. But fallocate is a way to tell a file, if you have ext4 or an XFS file system, to say, listen, this is going to be a 100 megabyte file, just pre-allocate 100 megabytes. And what we do is we allocate fallocate about 10 megabytes at a time. And the advantage of this is that if you have multiple writers going to the disk and they're each allocating as on small extents, or if they're not an extent-based file system, you'll get a fragmented file system, and that's really bad for performance. Yes.
So is that similar to Hadoop's block ID of allocating the page 64 blocks that you allocate basically?
The 64 megabyte blocks?
Yes. Is it similar to this ID?
Similar, yeah. The Hadoop 64 megabyte blocks are now allocated, I think, through fallocate if you have their JNI patch.
I think the big difference is that even if Hadoop is allocating 64 meg blocks, if you're writing multiple 64 meg blocks file system, the page allocations on disk will be interleaved. So you're not going to get contiguous pages. So when you go and read that back on disk, you're going to seek. With that allocate, you do all the page allocations ahead of time before you write anything. So when you finally do the write, it's all contiguous on disk. Okay. That's the advantage you get.
Yeah. So what we do is we allocate in 20 megabytes as we're writing. The other thing we do is f-advise, and so primarily we don't need pages, and I'll go into this in a minute. But the advantage of f-advise is that if you have a page and let's say you take a 100 megabyte file, and there's no, the box has 100 megabytes of memory free, and you cap that to dev null, it'll just be sitting in the page cache. That might be good for some situations, but it also might be bad. So what we do is in some situations, we f-advise away that data. So if we know that it's a temporary file, it's in the middle of a job, and we know we're not going to need it again, we just f-advise it away, or we can delete it. The other thing is that all I/O is async I/O, and we base our library on Netty. Netty is actually a really great async library. It's all done through HTTP and supports pipeline writes. The advantage to doing async I/O, especially with Netty, is that when we start to scale to larger installs, the C10K problem will start to become a problem, and we'll need to make sure that we can actually get decent performance. We do all memory allocation outside of the JVM. We don't use the heap as much as possible, so just use it for basic class files. Everything else is mmapped or mlocked or anonymous mmapps. We do use the other example of doing this is sendfile. You can mmap and then you can use sendfile, and for clients that are reading from PFS, we use sendfile, and it's 0 copy, and it goes right to the networking interface, right from disk. So it doesn't use CPU. Our strategy for memory generally in Peregrine is that we don't ever want to use a VFS page cache. It just ends up, we don't really need it. For a map reduce read, it's almost always contiguous I/O, and the files are so big. If it's like a 250 gigabyte file, it's not going to fit in memory anyway. And by the time you read the end, if you need to read it again, only the end is going to be in cache, not the beginning. So we've taken the strategy of using the memory for other things. For example, shuffling, the combiner, and page compression. Generally the strategy is when you configure Peregrine, how much memory, figure out how many worker nodes are on there, figure out how much memory, and then just allocate everything to these three setups. Again, I think, we talk about operating system integration. We, almost all times, we try to go for native operating system optimizations. A lot of this is Linux. We're deploying on Linux. Definitely not Windows, but maybe some Open Solaris stuff if people suggest it. We do mmap and MLock, as I mentioned. Try to keep data outside the virtual machine. It does things like send file. If we were to keep data inside the virtual machine, we can't, and we wanted to write it to the network adapter, for example, we would actually have to copy it from user land into the kernel and then move it out. But with send file, we can actually just read from the file and write it out directly. F-advise, F-allocate. And we're all doing this through JNA. That's really, JNA is basically about the speed of C right now, which is nice. So you can call mmap and MLock at the exact same speed that you would call C, which is kind of cool. You can kind of think of this as a distributed I/O scheduler. And I kept trying to think of the best way to view this, because we're doing some silly things, frankly, that you would not do in other situations. And I'll go into this in a bit. But basically, our theory is don't assume that the operating system is going to do the right thing. So a really good example of a problem we ran into is that when you're doing writes, and you're doing sequential writes, they go into the page cache. And then the page cache is eventually evicted when either the page cache gets more pressure or you call sync. The problem happens is what ends up happening is that if you do a bunch of writes, you write like 250 gigabytes to page cache, and now you come around and you want to do 250 gigabytes of reads. Eventually, the kernel is going to say, those pages that you dirtied, I'm going to evict them. But it's going to evict them while you're doing the reads. So what ends up happening is that your perfectly set up sequential write operation and your sequential read operation is now pseudo-random, because you have your reads operating, and then the page cache goes, oh, I got to evict this page. So now I have to seek over here, write this page, and then I have to go back to reading. Okay, and I have to write this other page. And so, and you don't really know what order it's going to write the page. It might not be the order that it's actually writing them on disk. So we actually saw this in production, especially in between job steps. So what we did was that we do periodic sync and f-advise while the jobs are running. And we implemented a barrier system, so that way when you're between barriers in a general operation, you sync the previous I/O, so that way the next time around the all the pages get evicted from all the dirty pages get evicted from the page cache, and then if the reads when the reads do go in the page cache for doing a read, which they have to anyway, you don't have to worry about competing for IO, which is much better. Peregrine has this concept of broadcast values, which is Twister supports them, and I think Hadoop. But generally, in a partition setup, what you end up having is you're going to want to emit small values for every node, and have those values generally, like, sort of think of them as globals in an algorithm. And the way we've implemented is that where they're basically reduces. So during your map reduced phase, you just implement values periodically, and after a map reduce, you run another small reduce, which takes like 30 seconds or 20 seconds, and it sums up all the you basically broadcasting these values, and then you reduce them, and you're able to read that value everywhere across the cluster, and it has a global value. So I think a good use case, a good example of this would be like, say you have a graph, and it's just a normal Twitter graph or a blog graph, and you want to know the number of nodes in the graph, but you need that, in a partition setup, you only know the number of nodes in your partition. You don't know what the global number is. So in order to find that, what you can do is you can run a MapReduce job, and then periodically, for every chunk boundary, you can say, listen, that chunk actually had, 100 million or 5 million keys. So you just emit 5 million. And then the reduce job takes all those values and sums them up, and then we broadcast them. So every partition then has a file with the global value. And that works really well for, like, for example, for PageRank, the number of nodes. You actually need the number of nodes globally in the cluster to execute PageRank. So we're then able to fully decouple the PageRank computations on the local node, because the local node has its local data, which they can merge across, but it can also read these global values. And for PageRank, it turns out to be the number of nodes and the current teleportation rate. Twister also implemented something which I think they are either called globals or broadcasts, I forget. But the concepts are almost identically the same. The interface for Peregrine is slightly different from MapReduce in that we have a struct reader. We use structs, which are basically byte arrays. And this is the familiar map with a key value. We also support reduce with a key and values, because it's you reduce these, you take these values and they're reduced, obviously. But we also support this new thing called merge. And I was talking about MapReduce merge. And what you do in the situation of merge is you'll have two files, and each file's values will be an entry in this list. So if you have the first file will be the first entry, and the second file's value will be the second entry. They obviously will have the same key because they're being merged in a merge string. The controller is the primary executor for the job. This isn't like there's no real master like in Hadoop. You basically embed the controller directly in your code, and it starts up when you want to execute your job. The worker is configured to know what the controller is, so you can only run the controller on one host. But this prevents someone from accidentally starting up another host, when it's not supposed to be run. And then the controller will only accept work from that controller while it's up. Once a job is running, it can then accept another job. And launching jobs is pretty. The API is somewhat simple. You basically give this is the map class, and this is a PageRank. This is what computes node integrate. And you create an instance of the controller, and you run the map function, and you just give it input. This is a variable we specified on the command line, and then you tell where to output. And the shuffle default is a Peregrine construct. We support multiple shuffle targets, so which allows you to do some interesting things. Like you could emit two different values periodically to different shuffles, and you could reduce over different shuffles, which can be kind of cool in some situations. And you can see that this shuffle default is the input to this reduce. So this reduce function knows where this shuffle is on disk, and will then be able to read the value. And you can see it's the same job, but this is just a reduce function. And then we write the output goes to this temporary file called node integrate. And after the map after this map job runs, this file will have the node integrate of every value in the cluster. This is what a merge would look like. In fact, both of these examples are from our PageRank implementation. So this is the node metadata, and basically what it takes is two files. It takes the node integrate and it takes the graph. And then it writes a metadata file, which combines the integrate and out degree. But we also write some additional files. One is a dangling vector, which is specific for PageRank, and another one is nodes that aren't linked, which you need for PageRank to do teleportation. And then we write two broadcast values. And notice they're very similar to shuffles in that you can name them. So when you write these files, you can reduce over these shuffles and they can write the broadcast values. I think I need to hurry up here. Sort of running out of time. Struct reader is a simple type system. It's basically all backed by disk. We needed a way to easily implement types. It supports mmap. You can read from files, read from memory. You can join the readers. It supports hash codes and varants. It's very much sort of a requirement for our setup because the source of some of these values can be from different positions. But it's mostly from mmap or nmap or yeah, it's mostly from nmap. Sometimes it's from memory if you want to give it like a literal, like this. Like this example, this would be from memory, right? We support hash coding directly. And this was an example of just writing a key value for myself. That's my last name, and that's the key. And I just create a hash code so it'll be stored, the hash code distributes the bits, so we can distribute evenly across the cluster. And then I wrote my age, no comment. And then I wrote my first name and last name. And then I write that to the cluster in key values. And then this would be a map function that you would write to read them out. And then key value, and then you just read. The age is the first value, so you call read int. My first name is the second value, so called read string. And the last is called read string. Pretty simple. One of the things that Hadoop has actually spent a lot of time on and does much better than we do is that they support lots of different data structures, data encoding formats, I should say. One of these is protocol buffers, another one is called avro. It's basically, I'd like to see it supported in the API so that you could do things like this, where both of these would be a protocol buffer, but we're not really there yet. I really don't want to compromise anything to get this. You could do it right now by just taking a struct reader and reading all the bytes in and decoding it through as a protocol buffer. In the core of the whole system, the whole system is just bytes. So whatever you want to store in a byte, it's fine. And we generally, we're just running on cheap commodity hardware, 816 core machines, 3264 gig, normal stuff. You generally want to run like more than one drive because if you have 16 cores, you might want to run 16 instances with like a gig each. But if you're running 16 instances on one drive, the performance won't be won't be that good. So 4 to 8 drives is probably more ideal. Failure detection is obviously exceedingly important, and we need to be able to handle when a node goes offline. So the workers send heartbeats to the controller. If the heartbeats, we don't get any more heartbeats, we mark it offline. We also have a gossip protocol when workers fail to shuffle, which is the other main component in communication. The controller, if it communicates immediately, it gossips to itself basically. Like so, if it goes to hand out a job and it can't send the job out, it just gossips to itself. And when the workers go to shuffle, when they're doing direct shuffling, if they try to write to host 002 and it can't write and it gets an exception, we contact the controller and we send and we can't work with host 002. You can see it right here, highlighted. When it gossips, we use voting to basically say, that machine has been marked offline. We just mark it offline, and the scheduler basically re-executes jobs on the secondary partitions, which I outlined before. We have a local mode, which is really nice, and so we embed. You can start up Peregrine with like a 16-node cluster on your laptop and simulate those modes. Not super fast because it's doing random I/O, but it works. we have really extensive unit testing that takes advantage of this. For example, we embed like 2 workers, 16 workers, 2 replicas. We tried it. We like all these exhaustive unit tests based on this. So our plans for world domination. I think right now you can kind of view Peregrine, especially once we get to 1.0, as more of a PageRank or a k-means engine. If you want a really good and super fast implementation of PageRank to k-means, you probably want to use Peregrine. We don't have k-means implemented just yet, but PageRank is pretty much done. And if you wanted to run these workers and run the controller and execute on a fairly large graph, it would work. I'd also like to have third parties do it, but I think right now it's a little bit hard to swallow because Hadoop has had so much done behind it that unless you really need an iterative job, you probably just do Hadoop. Its current status, we've released 0.50. It's production ready, but there's no Cassandra support. 0.55 is we're pending release. It does have Cassandra support, and it does have a full PageRank implementation. 0.50 is PageRank implementation is broken. But there is one bug in 0.55 that's preventing release. It has a memory leak, which I got to track down. Probably get it on Sunday. Future work. Right now, there is no combiner within Peregrine. That's a real weakness. We need to fix it. The original MapReduce paper showed that there was about a 40% performance boost when they started implementing combining. We have a branch for it, and it's about 85% of the way implemented. We're going to use a slab-based combiner strategy where I thought about this problem for a long time. It's completely different when you're in the world of direct shuffling. So it's hard. It's actually a really hard problem. But the way I'm going to solve it basically is that you write to a buffer and you take a 5 megabyte, you take the first 5 megabytes, you combine it, and then you write it out, and that's it. It should be perfect, actually. Talk about it a lot. There's some trade-offs, obviously, but it's not perfect. A better pipeline API, so that way you can just construct jobs as you would think about them, and then Peregrine will basically compile them down into the MapReduce representation of them. We don't support speculative execution right now, so that's another major advantage. It's mostly done, maybe 95%, so we're really close. The speculative execution is what ends up happening is that, let's say you have 100 nodes in a cluster, and one of your nodes is just running slightly slow, or maybe even 10 of them are. So what ends up happening is you have these stragglers that they're taking forever. So they're taking forever, why don't you just execute those same jobs on machines that are running fast? And if the machines that are running fast finish, you use the results from them, and then you just kill those other machines. Google, the numbers were very similar with regards to this performance. It was something like 20 to 2,000%, because some of the nodes, if you have a failed I/O controller, for example, and the I/O goes from 100 megabytes per second to 2 megabytes per second. In that situation, that would be a major speed up to switch that to re-execute those units of work on another machine. It would be nice to support a more general MapReduce runtime, while we're trying to stay focused on a really nice niche that Hadoop doesn't do a very good job at. If we can get Peregrine sort of rock solid, I could see people using it for jobs other than just iterative jobs. Better rack awareness. We don't really have rack awareness right now, other than deploy the default configuration in the correct rack setup, and that will work. But if, on failure, we wouldn't know how to correctly where to put the backups. Controller recovery. This would be so that way if the controller process crashes, you can just re-execute it. This is actually not that bad because the controller is just a finite state machine, and so we just have all these states, and I'm planning on just writing them to a log. And then when we resume, we replay the log, and the controller should be in the right state, and then they can just re-execute the jobs. Yeah. Oh, and compression. And I think that's it. I'm done. Is there any questions in the 3 minutes? Did a good job filling that time. Yeah.
So Hadoop has this whole range of different languages that you can use to write the MapReduce function in.
Oh yeah.
Right, Java, the streaming interface, the big. So what language do you actually write the MapReduce jobs in Java or
Just Java, yeah. You just write them in Java, and then when you compile your application, you just need to, and you start the worker, you just need to make sure your jobs are in the class path, and you can instantiate them and run. Yeah.
Forgive me if it's obvious, but how would I decide when I want to use an ETL-like engine like Peregrine versus when I'd want to use a stream processor like Storm?
Oh, that's an interesting question. Well, I think for Storm versus Peregrine, I think if you need the results immediately, you probably should run Storm. If you have a lot of data and you can probably wait like an hour or two, you probably want to use Peregrine. Like, I mean, Storm doesn't seem, and correct me if I'm wrong, but Storm doesn't really seem to be, wouldn't be super ideal for like taking a 500 gigabyte PageRank and executing. It's not really optimized for that. So, yeah, I mean, you would probably want to use Peregrine for something. So did I answer your question?
Enough? Yes.
Anything else? Any other questions?
no more questions?
Cool, that was a perfect presentation.
All right.
Thank you.
Thank you so much.